All right, guys. Well, hi again, Mr. A here, and now we're going to do the second video of our probability unit. And on this one, we're going to focus on mutually exclusive events and complementary events. Okay, so I'm on page 4 of the notes, and we're going to take a look at mutually exclusive events. So here is the idea for mutually exclusive events. When we talk about mutually exclusive events, we're talking about a single selection, okay? And on that single selection, mutually exclusive events cannot happen at the same time. All right? So, for example, if I'm tossing a fair coin, I cannot toss heads and tails at the same time. So, those are considered mutually exclusive. Another example is listed here on your notes. If I'm rolling a 4 or 5 in one roll on a number cube, I cannot do that. That's not possible. I can roll a 4 or a 5. I cannot roll each one of them at the same time in one roll. Okay? So those are mutually exclusive events. All right? So the big thing here is that mutually events occur on a single selection. All right? So we're talking about one pick. All right? And notice, okay, we're using the word or between the two events. It's there and it's there, okay, in the language. So when I am finding the probability of a mutually exclusive event, I'm going to take the probability of event A and add that to the probability of event B, okay? So we're going to add the fractions representing the probabilities. That's different from the previous video where we multiplied the probabilities together. Okay? The difference is the word between the events. It's A or B here. Before it was A and B. Okay? So when you see the word and, you're going to multiply the probabilities together. When you see the word or, you're going to add the probabilities together. Okay? So let's take a look at our example for mutually exclusive, and it's example 4 here. And we're going to use playing cards. Now, I'm not sure how familiar you are with a set of playing cards, so I'm going to try to help as much as I can here, okay? First of all, you need to know that in a regular standard deck of cards, there's 52 cards, okay? We're not talking about the jokers, we're just talking about all the playing cards, okay? There are 4 suits of cards, which means there are 4 different symbols on the cards. So if you divide 52 by 4, you'd get 13 cards in each suit. So let me go ahead and write the information down for you here. So you have this for reference when you work these problems. So 13 cards in each of 4 suits. Okay? Now, I'm going to make a list of all the possible values of the cards in each suit, okay? So each suit contains a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10. It also includes a jack, a queen, a king, and an ace. Okay? Now, that's all the values of one suit. And I said there are 4 suits. All right. The 2 of the suits are red and 2 of the suits are black. So the symbols on 2 of the suits are colored red, and on the other 2, they're colored black. So we have a diamond. That's one of the red suits. A heart. That's another one of the red suits. We also have a club, like so. Okay, that's a black suit. And then finally, we have a spade. Okay, so those are the 4 suits. So each of the values that I have in the list here, 2 through ace, are also in each of the suits. So there's a 2 of diamonds, a 2 of hearts, a 2 of clubs, and a 2 of spades. And it just repeats for every additional value in the deck. Okay, 4 of each value, and then 2 of each color. Hearts and diamonds, again, are the red colors. Clubs and spades are the black colors. And that's how a deck is formulated, a regular playing card deck. Okay, so what we're going to do is we're going to select a card, one card, okay, from a deck of playing cards. We're going to select that card at random, and we're going to figure out these probabilities down here. Okay, so again, I'm going to work problems 1 and 2 this time, and I'll leave you to work problem number 3. Okay, so you have that problem to work on your own. All right, so problem number 1, what is the probability of selecting any ace or any king? All right, so I'm going to help you out with the count for any ace, okay, and then I'm going to leave it to you to figure out the count for any king. So for any ace, I just said there are 13 cards in each of 4 suits, so each value in one suit is the same for the other 3, so there's going to be 4 of each value, 1 of each suit. So for the for the aces, there's going to be 4 of them. There's going to be 4 aces, 1 of each suit: the ace of diamonds, the ace of hearts, the ace of clubs, and the ace of spades. Okay, so there's going to be 4 aces. Okay, and I'm going to pause for a second, and you're going to figure out how many kings there are in the deck. Okay, so pausing now. Okay, and if you did it correctly, you should have figured out that there are indeed 4 kings, using the same logic I did with the aces. Okay, so we're going to figure out this probability. Okay, so it says any ace or any king, so we're going to be adding these together. So if you want to put a little plus sign there, that's fine. There are 4 aces out of 52 cards in total. Okay, and likewise, there are 4 kings out of 52 cards in total. All right, so if I add these together, I'm just going to add the numerators. Remember, when I add fractions, I just add the numerators. The denominator stays the same. So I have 8 over 52. All right, and it helps to add these up if the denominators are the same from the get-go. So don't reduce these until you've added, because it makes it a lot easier to add them. That can be reduced. They're both even numbers. In fact, they're both multiples of 4. So we're going to take out the multiple of 4, and it becomes the fraction 2 over 13. Okay, so there's the final answer for problem number 1. All right, I'm going to give you a chance here to figure out problem number 2 before I go into it. Okay, so I want you to read it, and then we're going to discuss how to get your counts on the other side. All right, so give it a try, and then I'll meet you back here and after you unpause. Pausing now. Okay, so remember that, again, the situation is reset. So all the cards are back on the deck. Okay, so we took the aces and kings from the previous problem and put them back in the deck. So there's 52 cards again. All right, so it says, what is the probability of selecting the 7 of spades or any heart? Okay, so the 7 of spades, there's only 1 7 of spades, which means there's only 1 7 with a spade picture on it. Okay, so there's 1 7 of spades, so I'll make a list. 1 7 of spades. Okay, so there we go. So that's going to be 1 over 52. And then any heart. Well, there are 13 heart picture card, or there's 13 cards in the deck with a heart picture on them. So we'll have 13 hearts. Okay, so I'll take 1 over 52, add it to 13 over 52, and I will add these together. That becomes 14 over 52. Okay, and again, we can reduce this, divide by 2, and I get 7 over 26 for my final probability. Okay, so on problem 3, you're going to find the probability of selecting any black card or any 4. So give that one a try, check your answer with the answer key, and see how that goes for you. Okay, now to wrap up this video, we're going to look at page 5 of the notes. Okay, and page 5 talks about complementary events. Okay, so I'm going to scroll this up here. So similarly to mutually exclusive events, 2 events are complementary if, again, they have no outcomes in common. But here is the difference between mutually exclusive and complementary. Complementary events take all the possibilities of a situation into account. Mutually exclusive, again, it's just for one selection, okay? So that is the difference there. If you take all the probabilities of a single event A and add that to the complement, that always equals one whole, or 100%. So you're accounting for all the events and their complements add up to 100% or one whole, okay? So that is how we figure out complements of events. Now, the way we write that in short term is with the word not. So if you see P of not A, that stands for complement. I don't want to count event A. I want to count everything but event A. All right, that's how we reason through that a little bit. All right, so on example 5, what we're going to do is I'm going to work examples 3 and 4 this time, and you're going to work examples 1 and 2. Okay, so for examples 3 and 4, we're going to use this situation where I have this phrase of math rules. Okay, we're going to select a letter at random, and then we're going to express each probability as a fraction of lowest terms. Okay, so what I want to do is, first of all, I want you to figure out how many different letters I can select from to get our total number of events, and then we'll look at problem number 3 and talk about that language. Okay, so pausing now. Okay, if you counted correctly, you should have figured out that in the phrase math rules there are 9 different letters. So 9 letters total. Okay. Now, we're going to skip to problem number 3. Okay, so problem number 3 says, what's the probability of selecting a letter from that phrase that is a vowel? Okay, that is a vowel. Now, if you remember, in the alphabet, there are 26 letters. Okay, and 5 of the letters are vowels. All right, so I'm just going to make a little note over here at the top. Okay, the vowels are A, E, I, O, and U. Okay, Y does not count as a vowel. All right, so it's A, E, I, O, and U. So when we are looking at our phrase, we're looking to see how many of those letters fit the condition for being a vowel. All right, so there are 26 letters, 5 are vowels, 21 are not vowels, those are called consonants. Okay, so in our phrase math rules, okay, I want you to identify how many letters in that phrase are vowels. Okay, so I'm going to pause for a second and let you figure out how many of those are vowels. Pausing now. Okay, so what we should have figured out was that 3 of them are vowels. Okay, if I'm reading left to right, 3 are vowels. Okay. Okay. All right, so the 3 vowels in the phrase are A, U, and E. Okay, so the probability that I'm going to select a vowel from the phrase at random would be 3 over 9. And if I can reduce that by 3, I get the final fraction 1/3. All right. Now, on problem 4, this is the complement of problem 3 because I have the word not in there. Okay, so basically, I don't want to pick a vowel in my selection. So if 3 of the letters are vowels, then 6 must not be vowels. Let me write that again. That's a little sloppy. Okay. And again, a letter that's not a vowel is called a consonant. Okay. And here is the list of the letters from the phrase that are not vowels. We have M, T, H, R, L, and S. Okay? So 6 of the letters are not vowels. So I'll have 6 over 9, because again, the situation resets. I can divide that by 3 again, and I get 2/3. Now, if I take the probability of selecting a vowel, which is 1/3, okay, and then take the probability of not selecting a vowel, which is 2/3, I get 1/3 plus 2/3 equals 3/3, and there's my 1 whole. Okay, so the probability of an event plus its complement always will equal 1 whole, or 100%. Okay, so go back now and try problems 1 and 2 using the same kind of idea. Okay, selecting an R, then not selecting an R. See if it works out that way as well. And that's going to do it for this video. And we have, on the next video, we're going to start talking about some different counting techniques that we can use to make sure we get all of our outcomes accounted for correctly. All right.